Let's master RMS Norm. It's used in large language models in today's neural networks and transformers everywhere, and it's very popular normalization. I think the most popular one today. Here is what it does. If we have a vector of some numbers 1, 2, 3, 4, 5, we're gonna need the mean, which is 3, and standard deviation, which is just a way to measure how far away these numbers are from mean. And standard deviation is one way to do it. We have many other possible ways to do it, but this is just a standard way to do it. So this single number, standard deviation, will tell us how different these other numbers are from mean, because we could also have mean 3 if we had some other numbers here that are further away from 3. Then the mean would still be 3, but this number would be a lot higher, because then those numbers would deviate a lot more from the mean. And you'll see here that after we apply RMS norm to this vector, this is the vector that we will get. And it goes from 0.3 to 1.5. So the purpose of RMS norm is to make all of these values kind of close to 1. So in neural networks, they don't become too small or too big, so we have vanishing gradients, exploding gradients. And in large language models, this RMS norm is applied before every attention block or feed-forward block, and it's used in a lot of other models, especially transformers and other similar models. Because numbers around 1 make neural network training better, faster, less unstable, less issues with exploding, vanishing gradients, etc. So one person in my Discord, where we research LLMs and other stuff, found out that in some cases applying RMS norm to both before and after attention and feed-forward network makes the training better. Usually most of the time it's applied only before. But we are still doing this research, so you can also join. Link below. So the way RMS norm works is we first square each of these inputs. So these are the squares, 25 is, and then mean of the squares 11, and then square root of the mean. So this is RMS, the root mean square. And it's kinda in the opposite order. So this is root mean square. And then divide input by RMS to get normalized output. So we divide each of these numbers by our RMS to make them closer to 1. Join my school to become AI researcher with the community. These are all of the courses, and hurry up because it's free for now until I build a bit of base community, and then it's gonna become paid, so hurry up. And here in the code, you can see the same function. X is the input, and epsilon is a very small number to prevent division with 0. You always have this. So here we have our array, mean of our array, but we will first square all of the elements in the array and then find the mean of those squares. And in case that this is 0, I guess we add epsilon. This is not for division then. This is so we don't do square root of 0, although that also exists. So maybe this is the practice here, but I would guess it would work without adding small epsilon as well. Oh, no, because we are dividing here with this number. So if we take square root of just 0, it will be 0. So then we will divide with 0. So that's why we don't want to take square root of 0, we want to take at least some small number. And down below I have the same thing but with PyTorch. And in PyTorch we're also gonna have these learnable weights. And you see here at the bottom, once we normalize at the end, we multiply our x with the weight tensor. And so it's an element-wise multiplication. So we have the scaled tensor, normalized tensor, and then first element of the weights will multiply the first element of this normalized tensor. That will be the first element of our output. Second is the second, third times third is the third, etc. And these weights can fix some issues that can happen with normalization, because this normalizing can literally change the information contained within the vector. So because these numbers in the vector, still their magnitude tells something. So this will just learn to fix any issues that are created, or any loss of information caused by this normalization. So imagine that this RMS norm is used in the neural network transformer, and once it learns these weights, it will always have the same weights. So every vector that passes through this RMS norm will be multiplied with the exact same weights. So the purpose of these weights will be to change the output of the RMS norm a little bit, or even a lot, if necessary, for the neural network to learn. And the intuition is, as I said, that this could actually cause some issues, and these weights are to fix the issues, the side issues that could happen. And so the weights will be learned based on the architecture of the transformer neural network, and they will always be the same. And they will perform the same thing always on every vector. Here we trained a simple neural network with RMS norm, and I want to show you what it does. So during the training, we have 500 epochs over data. Here I'm plotting the weights of the RMS norm, and there is 4 of them. So this vector of weights has 4 values, and in the beginning they have these values around 1 on the plot here, and then later they learn these values. For example, 1.7, 0.8, 0.50 something. And we will explore why and how this happens. And here, during the training loss, we have a huge loss spike, and we'll try to figure out why we have this loss spike. Our simple neural network is just trying to learn XOR function, which, to simplify, so it has 2 inputs, so 2 numbers as input. And if it's 0, 0, it needs to output 0. If it's 1, 1, output 0. So if the numbers are same, output 0. If numbers are different, output 1. And so in the beginning, it's not going to it's not going to be these correct numbers. So in the beginning, it will start learning, and at the end, it will learn what to output. And this is minus here, minus 0, just because maybe this is a number just below 0, so it's learning that it needs to be 0. So I'm importing torch and numpy and matplotlib for plotting. Our RMS norm is same. So we actually start with all ones. So 4 of them, 4 ones. For these weights, parameters, and then it will learn whatever I showed you earlier in the graph. But this is that RMS norm operation that I was explaining. Same. And then simple neural networks, so fully connected first and second layers. So first goes from input dimension, which is 2. We have 2 numbers as input. Hidden dimension, which is going to be 4. So we want to expand a little bit so neural network can memorize data and learn the rules in this hidden layer. And output is just 1, so 0 or 1. So we will also define RMS norm and normalize the hidden layer in this case. And we have just 1 layer, so we'll just normalize this 1 layer. At the end, we have ReLU activation because our task is not linear. You can check my video Neural Networks from Scratch or Neuron from Scratch to understand better the intuition between these. And so this is just the defining, but here we pass it through the forward. So first through first fully connected, then RMS norm, then ReLU. And that's what I thought. I thought like we are defining ReLU last here. So I was thinking, why do we put ReLU last? It doesn't make any sense. But here we actually put it after RMS norm here. So now it makes a lot more sense. This is the actual forward pass. So this is the training data. If we have 0, 0, output is 0. 0, 1, output is 1, etc. So we define model we define criterion, which is our loss function, and optimizer. And then I'm going to keep track of the RMS norm weights and loss history. I am printing here initial RMS norm weights are 1111 and final RMS norm weights are these. This is what the model learned. So this loss spike might be due to Adam optimizer, and you see this is extremely small numbers. So I guess this loss spike is actually very small. I'm gonna make a video about Adam optimizer in the future. So drop a subscribe. We're almost at 10K subscribers, guys. Subscribe. Join my school to become AI researcher. You can introduce yourselves here. You can post about your research, etc. or whatever you are learning. And we have lessons here that you can learn from. It's still free to get the initial community, but I'm gonna make it paid soon, so hurry up. That's it for this video and see you next time.